So it's actually not that long of a section. And then we're going to start a little bit of 11.2. I'll pass that out. Then we should have about at least 20 or 30 minutes to talk about the test a little bit. Okay, so what we're doing on this 11.1 to begin with, the first thing is we want to look at what E is, the mathematical constant E. We've talked about that briefly, because one of the things we're going to get into is exponentials and logarithms, which are actually a pretty big deal in economics, because exponential functions show up a lot. Okay, so what I want you to do on this is get your calculator out, and please do this along with me. Okay, we're going to do a graph. So I want to kind of help you understand what E is.
The screen's not on.
What's that? Oh, that might help. Okay. Unless you want me to just teach this way today. Okay, hang on just a second. So, yeah, let's get calculator out. And we're going to do a graph. So what I'm going to have you put in is this function right here. Okay, we're going to take a look at that. Okay, all right. So and you're going to put it in like this. You put in parentheses, then 1 plus 1 divided by x. Okay, you got to put that in a parenthesis like that. And then once you have that, you want to use your raise to a power. You're going to raise to the x power like that. Okay, and then I'll give you a window to kind of help you set this up then, because I know what's going to happen. I'm going to show you what's going to happen. Okay, so let's do that. Now your window, you want to go 0, and let's just start by going to 10. We're going to start by going to 10 and then scaling that by 1. And then the y, we're going to do like 0 to, let's say, 4. That'll allow us to see what I want you to see, and then scale by 1 like that. Okay, and I'll slide that to the side. Okay, so if you need to get that put in. Once you have that put in, go ahead and put graph, and you'll see a function that kind of has a starting point, then it kind of looks like it levels off. Does it look like it levels off and maybe has a horizontal asymptote? Okay, that's what we're going to kind of look at. Okay, now what I want you to do on your graph, because I do want you to just kind of have a little sketch of a graph on this, let's label this x and y. And let's go out to 10, and you can scale it like that if you want to. And let's see, we're going up to 4. It's kind of like that. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Okay, now let's just trace out a couple of points. Okay, just enough to get a pretty good idea. The other thing you can do is you can just go second graph. So if you go second graph, let's just open up the table on this, and let's just plot some points. So the first thing is we have an error when x is 0. Do you guys know why? Look at what we graphed. Is there a problem? Right here. That's a problem, isn't it? Okay, you can't have 1 over 0. That's why there's an error. Okay, we're undefined there. Okay, so let's go on. It looks like we got one kind of nice point here. We have a point 1, 2. So let's plot that point 1, 2 like that. And then let's just maybe get another one. Go all the way to 10. Okay, if you go to 10, over 10, it looks like you're up about 2.5. Okay, a little bit above that. So I want you to just estimate that. And that's good enough. Let's maybe label this point as 1, 2. And what happens on this one is it kind of does something kind of like this. It gets real close to that. Okay, like that. Looks like maybe you even have an asymptote there, kind of like that. And then just kind of show like that it's kind of leveling off like that. Okay, so that's the idea of that graph. So this is a definition of what E is. So one thing I want you to know is E, you may know from your background, it's a lot like pi. So it's 2.71. It's got these decimals that go on forever. There's no repeating pattern anywhere. So the decimals just kind of go on forever without a pattern. And if you do this, if you notice, if you look at the table of values on this, when we got to 10, see, we're almost to 2.6, okay? So I want you to do one more thing with your calculator. Let's go back to your window, and I want you to go up to 100, okay, like that. Just change that to 100 and maybe scale by 10. Now, if you regraph that, you're just going to see the same thing, but you're going to see that thing, again, leveling off like this. So I want you to just go 0 to 10 now. Regraph it, You can clearly see that thing is just leveling off, okay? Now, let's do this. Type trace and type 100. So if you type 100, when x is 100, look where you are. You're at 2.70, but e is about 2.718. So it looks like we're getting close to e. What do you think? Okay, that looks like that's what's happening on that problem. So I want you to do one last thing. Go to y2 and then type in e. Okay, if you want to get familiar where everything is on your calculator, on your division symbol, you'll have the letter e. Like in the exponent, you'll have pi, so just go second division, and then you'll get e to come out. Now that's a constant. That's 2.7, so you're going to expect a horizontal line to come out. And what that is it's a horizontal asymptote. So the other thing I would like you to put on your graph is just kind of label this as e, and then put like a dashed line like that, and just make a note that you have a horizontal asymptote at y equals e. Okay, so one of the things is that's what e is. It's that function. So the other thing that I want you to write down on here is this. So we've learned about limits. So if you're doing a limit of this function as x approaches infinity, what does it look like it is? Looks like it's e, exactly. Okay, so that's a definition of what e is. Okay, it's basically that particular function. And I'm going to show you actually today how we call this, e is called the Euler number. A lot of times there's a famous mathematician. Well, if you're a mathematician, you know he's famous. So Euler is the person who kind of came up with this constant, and he actually did it with economics, which is kind of interesting. So I'm going to show you how he came up with this number. So we call that the Euler number. Okay, so that's what E is. You maybe have seen that a little bit, but maybe don't know where it comes from. Okay, like when I teach my Calc 2 classes, I teach them a lot where pi comes from. It's like what we call an infinite series, okay? So basically you're going to look at, this is what I just showed you. You have basically, it turns out that this is the same as this, and I'm not going to prove that or anything, but those are kind of two definitions of what E is. You can write them in terms of limits, okay? Now let's go to the next page. We're going to do a little bit of economics that hopefully you've done some of this in your background. If you hadn't, it's pretty easy to learn. So you basically have simple and compound interest, okay? We're going to focus mostly on compound interest in this section. So simple interest is just the interest is the principal times the rate times the time. What's the principal? That's your starting amount. R is the interest rate, and then T is going to be the time, like that, okay? So what you have on this simple interest, what it means is it's just done one time, okay? So it's kind of like if you were doing interest, and it's usually an annual interest rate, but it's just done once. Compound interest is done over and over again, okay? So the other thing I want you to know is this. This is the simple interest formula. So if you wanted to find the amount in a bank account after a period of time, well, what you'd do is you would take your principal, then you would add your interest, okay? So say like you have a savings account. You put money in, you're earning interest, so what do? You add the principal to the interest, right? Okay, what's the interest though? The interest is PRT, so I'm replacing that I with PRT. Okay, so I'm just taking the original principal and adding the interest. Does that make sense? Okay, now what did I do to go from here to here? These are all the same formula. All these formulas right here are mathematically equivalent. What did I do? I factored a P out, right? Okay, so I just did some basic algebra. So the most common way that you would see this simple interest formula for relating the amount after interest to the principal you started with is that, okay? So let me give you an example on this. I'm not going to do much simple interest, but let's just say, and write this down, let's just say, for instance, your principal is, you decided you were going to start a savings account and you just put $50 in the bank, okay? And let's say that the interest rate is, say it's 2%. Savings accounts don't have very high interest rates typically. And then let's say that you want to find out how much money you're going to have after 50 years. Okay, this is your retirement savings. You obviously aren't going to end up with much money on this, but I want to show you how simple interest works. There's two ways to look at this. First way is you can just compute the interest by doing PRT. Okay, you can do it like that. So if you did that, the principal would be $50. Now the interest rate, you have to change that to a decimal. What would that be? 0.02. Good. A lot of times students don't do that right. You got to move the decimal back to the left too. Okay, because 2% is just 2 out of 100. Okay, anytime you divide by 100, the decimal moves to the left too. So then you would do that. Okay, then you would take your 50 years. Okay, and see, basically in simple interest, this is really a per year thing, is what that is. And then everything units match up. So what I'm going to do from here then is, let's just calculate this real quick on the calculator. So we have 50 times 0.02 times 50 years. So if we're talking at what in the world did I do wrong there? Did I do something wrong? Oh, that is the interest. So it would be 50. That's kind of weird, but that is right. Okay, because I'm just doing 50 times the 0.02. I didn't expect it would turn out that way, but it does. Okay, that's just a coincidence too. So that means the interest is $50. Okay, like that. So I want to show you how all these formulas work. So now, if you want to find the amount in your bank, well, okay, what do you do with those two numbers? You add them, exactly. So we do the principal plus the interest. So that's equal to $50 plus $50. So now you've got $100 in the savings account. That's just because 50 years is a long time. Okay. Now you can also use this formula. I'm going to just have you use this formula also, and I'll just show you get the same answer. So plug in the P, which is 50. Then you have a principal 1 plus interest rate's 0.02. Time is 50. So if you work that out, you should get exactly the same answer. Okay. So what happens on this is when I go to my calculator, and if I do what's in the parentheses here, I would do 1 plus 0.02 times 50, like that, and then that's going to give 2, and then 50 times 2 is going to give $100. Okay, so that formula works out. So the most common thing that you see a lot of times in textbooks is this is a formula for the amount after interest if you have simple interest. But you can do it either way. It doesn't make any difference. Okay, does everybody follow that up, what I did on that okay? Okay. Now, compound interest is what we're going to focus mostly on. And what compound interest does is interest is done over and over again. It may be monthly or something like that. For instance, on my mortgage, okay, every month interest is charged, right? Okay, or if you get a loan for a car, most of the time, every month interest is charged. You can charge interest daily, quarterly, annually, all kinds of things, okay? So here's the compound interest formula, and you want to know what everything is in here. A is the amount after interest, P is the initial amount, R is your interest rate. But what's different about this is M is the number of times you do interest in a year, okay? So if you did interest monthly, then you would do 12 times a year, right? If you did interest daily, it would be 365, although some financial institutions do 360, okay, as a kind of a common practice. So it goes like this, and then T is your time. So let's work with the compound interest formula just a little bit here. And I bet a lot of you have done that. Is this true?
This was the last section in finite.
Yeah, finite, you do that. And if you've taken any business so far, you may have already done some of that. So that's helpful. Okay, so let's go ahead and do this then. So what you're doing on this one is, now this one is kind of interesting. So we're going to have the principal is going to be what we start with. So we're going to start with $1. I'm picking these numbers on purpose for a certain reason. Okay, and then we're going to have the interest is going to be 100%. Okay, so what would happen if you moved the decimal back too? What would you get? You get 1. If you had 100% interest, you'd have 1. I'm doing this problem because it's going to give us an interesting result. Okay, and then the next thing we're going to have is the time is 1 year. That's what the problem says. And then it says we're doing this annually. So in your formula, M is how many times you do interest in a year. So annually just means 1 time. Okay, that means every year. If it was monthly, it'd be 12. Okay. So let's plug into the formula and let's see what we get then. So it would go like this. The principal P would be 1. So you put your 1 there. Then you have 1 plus R. R is 100%, so that's 1. M is 1, like that. Okay, now go to your exponent. M is 1, and T is 1 like that. Okay, everything's 1. Okay, now we're going to just do this on the calculator and see what happens. So we have 1 times, this would be 1 plus 1 or 2 to the first power like that. We don't need to use our calculator on this. Okay, so actually what happens on this then is, this is not working the way I thought it was. I may have picked the wrong numbers. That's okay. So you would end up getting the $1 would change to $2 like that. Okay, so that's how that would end up going. I need to think about that maybe over break a little bit here, because the way Euler came up with the number 2.7 is he did this. E comes from the compound interest formula. So if you look at this compound interest formula, and if you look at what I had you graph a minute ago, don't they kind of look the same? Okay, that's actually how he came up with E. And I was thinking, there's something I'm missing on this. I was thinking he did $1 at 100% interest over a year, but I may be wrong on that. I'll play with that a little bit. It may end up being something else, but that was kind of the idea. Okay, let's go to the next one, and this one's a little bit more what you're going to do here. So it's a good idea as you're learning this to just kind of write down everything that you know. So this says how much money is going to be in an account after, so that means you're finding A. So P means that you're depositing $1,000. Okay, so we have that. Okay, and then your interest rate is 6%. Okay, and since that's compounded monthly, that means M is going to be 12. Okay, that you're doing something 12 times a year. Then it looks like the time is going to be 10 years like that. Okay, so we got everything that we need to have. Okay, I'm going to go and write down the compound interest formula. So its amount is P times 1 plus R over M to the MT. Okay, so let's just make sure you do this. You need to use your calculator on this, obviously. So the principal's 1,000. Then you have 1 plus, what are you going to use for 6%? 106, good. Okay, for M, that's monthly, so that's 12. Then you would have M is 12, and then the time is 10, like that. Okay, so you're going to have everything put in like that. So the first thing is you guys understand how everything's getting plugged in. Okay, now one thing that you can do on this is you can do a little bit of stuff in your, anything you can do in your head, I recommend you do that. So that exponent's 120. Now I'm just going to go directly to my calculator. And again, you want to do this in just one big step. You got a good calculator, got parenthesis keys, take advantage of that. So I'm going to do 1,000 times 1 plus 0.06, and then divide by 12, and then close the parentheses, and then raise to the 120th power. Now another thing that you can do on this is you could put another parenthesis and do 12 times 10 if you wanted to do it like that. But if you do it like that, that needs to be in a parenthesis, because if it's not there, it may not do the order of operations correctly. So either work the exponent out or put that whole thing in its own parenthesis. Okay, now press enter, and we should expect to get something bigger than 1,000, right? Okay, so what you would get on this is, okay, that's a good deal. That is $1,819, and then I'll round that to 40 cents. Okay, like that. Is that what you're getting? Okay. How much interest did you make?
819.
Right, exactly. So your interest is just going to be this amount minus the principal. So you actually earned $819.40 interest when you did that then. Okay? So that's kind of a standard example of how you use compound interest formula. Okay? That make sense? Okay? All right. Now, actually, a lot of times, like savings accounts and loans really work a little different. If you took finite, you may have learned the loan formula, and you may have learned the annuity formula. Is that true? Or those of you who took finite? Okay. Some of you may have learned some of that. Okay, those are things you learn in business classes a lot of times. So they revolve around this idea of compound interest. Okay. So actually a mortgage does not work this way. It works a totally different way, and typically loans work a different way than that. Okay, so let's do, go ahead, I'm going to do one more, then let you do a couple of problems. Okay, so, all right, so this one you're depositing $100, so P is 100. Okay, you got again a 6% interest rate. Okay, this time you're doing annually, so what is M? 1. Okay, right, and then time is 2 years. Okay, like that. Okay. So what we're going to have then, when you plug this in, again, you have, and you don't have to write the formula down. If that's helpful to you, you can certainly do that. Okay, just start plugging numbers in, get your calculator out, see what you get. Okay, so principal is 100. You have 1 plus 0.06 divided by 1. And then, let's see, M is 1 and T is 2, like that. So that's how that gets plugged in. Now, some of the stuff on this you could do in your head. So I'm just going to type this in as 100, then put a parenthesis. That's 1 plus 0.06. You can even just put 1.06 in, and of course your exponent's 2. So you would expect to get a number a little bit bigger than 100. So we get $112.36. Okay, so how much interest did you earn on this one in your head? $12.36. Okay, all right. Okay, so I'm going to have you go ahead and, well, let me talk about this first of all. So what I did is I took this out of the book because it's kind of a good chart. What we just did is we just found that amount. So semi-annually means that you're going to do interest twice a year, every 6 months. And then you get this. Quarterly is 4 times, monthly 12 times, weekly 52, daily 365. The most common practice a lot of times is 360. There's some reason for that, and I don't remember what that is. What's that? Is it holidays or something? Okay. I think that's the most common practice that I'm familiar with. I think what we're going to do in this class is just use 365 because that's what the book's going to do. And then hourly, well, you don't have to memorize it's 8760. You just take, 365 and multiply it by 24, right? There's 24 hours in a day. So what I want you guys to see, what's happening to your amount? It's getting bigger, isn't it? So the idea is the more often you do interest, the more you're gonna earn, right? That's the idea. That's the central idea to that we're going to develop. Okay, so go ahead and I'll let you guys take 2 or 3 minutes to just work the next 2 out. Use your calculator, see how you do on these.
So are we doing 365 or 360?
We're going to use, I'm going to go ahead and see if you're on the right track here. And if you're still finishing it up, you can go ahead and do that. So let's see, number one, let's see, you have $5,000 for your principal. The interest rate's 5.5%. So what did you use? 0.055. Be sure you always do that right. That's a place where students make mistakes sometimes. Times 5 years. Daily, what's M? 365, right. Okay, so when you set it up, you're going to go 5,000 times 1 plus 0.055 over 365. Okay, then your exponent is going to be 365 times the 5 like that. Okay, so what did you get? 7,000 and something? Okay. 6,000 and something? Okay. All right. Okay. Okay, you just want to make sure you're doing everything right on your calculator. So I'm going to put in 5,000 parenthesis 1 plus 0.055 divided by 365. Okay, and then raised to, see what I'm going to do is just use a parenthesis to do 365 times 5. So you want to control the order of operations. So you want the calculator to do what's in parentheses. So let's see if you're right. Okay, does this look good? $6,582.52. Does that look good? Okay, all right. Okay, next problem. The principal's 25, the rate's 15%. So you're going to use 0.15 times 50 years. And semi-annually, what's in? 2. Good. Okay, so you're going to have, I think I put that in the wrong spot there, 6582.52. So the next problem, you're going to have $25, 1 plus 0.15 over 2, and then 2 times 50 like that. Okay, so you should have got something bigger than $25. What did you get? Okay, that sounds pretty reasonable. And 50 years is a long time, so you're going to be making a lot of interest on that. So then you would have 1 plus 0.15 over 2. Okay, close parenthesis, and then 2 times 50 is 100. If I can do something in my head, I just do it in my head. Okay, whoa. That would be I like that bank, so what in the world did I do wrong here?
That's right. No, you're right. That's right. It's just 15% over 50 years. It's a lot.
That is a lot. 15% is a lot. Is that right? That just seems like crazy to me.
Twice a year?
Twice a year? $25. 15% is a nice interest rate, no doubt. That just.
We used to be able to buy savings bonds, and I think the interest rate was, I don't know, a little under 2% or whatever.
Yeah. You know, what happens on this, of course, it's doing interest on interest. And what happens is, like if you can actually do a graph of this kind of thing, and it goes like this. Your interest kind of starts, but then it starts going out of control. Once you start getting up into that 40 years, it starts taking off. So that's kind of surprising to me because of the
bigger and bigger, right? Because the
yeah.
interest amount goes back into the principal.
Exactly. So yeah, so the way compound interest works is you're always doing interest on interest. So it collects and gets bigger. So you would probably find it kind of starts slow, and then it just gets out of control. Is what happens. Okay. Well, if you can find that somewhere, go for it. That's awesome. Okay, so what we're at is, next thing we're going to look at is continuous compound interest. This may be something that you maybe have not studied, because calculus is helpful to know what continuous compound interest is. So without going through a lot of the details on a development or kind of a proof of this, the idea that I want to take you through is, you want to get this in your mind, is the more often you do the interest, the more money you're going to make in your deposit. And you could go beyond hourly. I mean, you could go secondly if you wanted to. You could go microsecondly. You could go picosecondly. And you could even go continuously. What continuously means is that every single instant of time you do interest. Okay? Now, what's happening on this thing, too, is this. This thing, by the way, is not going to go to infinity. If you look at this chart right here, if you went to secondly and just got the increments closer and closer, that won't go to infinity. It's kind of slowing down. Do you see what I mean by that? 74, it's not even gaining a penny now. It's just beginning to gain decimals. So you're going to find that there's a limit to that. So if you're doing interest continuously, that doesn't mean it's going to go to infinity. It's going to go to some amount. So that's one concept I want you to think about. The continuous compound interest formula is this. Okay, it's A equals P e to the RT, so it has E in that. Everything pretty much means the same thing. P is your principal, R is your interest rate, and a decimal, and then, of course, T is your time, like that. Okay? I always, to help you remember this, I don't know why I think of this, you know, there's a Pert shampoo, right? So it's the Pert shampoo formula, okay? Pert, P-E-R-T. Now, it's a real simple formula to use, so let's do this then. Now, we're not going to get infinite answers. We're going to get something finite. So on this example 5, we're going to use the continuous compound interest formula. So the principal is 1,000, okay? The time is 5 years. Okay, and I may have not given you an interest rate on there. Find the amount if the interest is compounded monthly. I need to do that. I forgot to type that on there. So let's just say we have an interest rate of something like 3.5%, okay? And then that's supposed to be compounded continuously. Why did I do that? Oh, no. I understand what I'm trying to do, okay? All right. Hang on, let's do this the right way, because I had a plan on this problem. So let's go ahead and let's say that the interest rate is 3.5%. We're going to do this problem in different ways, okay? So I forgot to put the interest on here. Okay, so if we're compounded monthly, we're going to go ahead and do the compound interest formula. So we're going to go ahead and do that a couple of more times. So if you do the compound interest formula for monthly, you're going to take the principal, and then you're going to do 1 plus the interest rate. So what's the interest? What are you going to use? 0.035. What? And then what are you going to have for the monthly? What do you put under that? 12. Okay. Then your exponent's MT, so it's 12 times 5 years. Okay. All right. Now I'm doing compound interest. I'm not ready to do continuous yet. I'm trying to make a point on this. Okay. So let's go ahead and put this in. Okay, on the calculator, so I'll just put in 1,000 for my deposit. Okay, then times 1 plus 0.035 divided by 12. And then 12 times 5 is 60. So let's see what we get there, and we'll just round to 2 decimals. Okay, so it looks like I'm getting on that about $1,190.94. Okay, like that. Okay. Now, let's do 1 hourly, okay? So let's go to the same problem, but let's do this hourly. So now what you're going to do is you're going to have, same thing, you'll have 1,000 for your principal, and then 1 plus 0.035. Now, when you're doing hourly, just do it like this, okay? Basically, you know that there is 365 days in a year times 24. We're going to use that number, 8,760. Okay, so 8,760, we'll have that. Then your exponent will be 8,760 times, how many years is that? 5 years. Okay, so go ahead and put that in your calculator. Okay. Now, is this answer going to be bigger than the previous answer we just did, or smaller? It's going to be bigger, and they are going to be close because you're doing interest more often. So we got 1 plus 0.035, then divide by 8,760, and then see, I'm going to put this exponent in a parenthesis and just do 8,760 times 5. That way the calculator is just doing everything in one step for me. So we should get something a little bigger. Okay, so it looks like I'm getting 1191.25. Okay, so it's growing a little bit. So the idea is you're going to expect that to happen. All right, everybody with me? Okay. Now we're going to do this continuously. Now when we do it continuously, it means every instant of time. So the answer is going to be bigger. Okay, and it's going to be as big as it's going to get. So now we do the Pert formula. So we have P(e) to the RT. Okay, so the principal is 1,000. You have E. Now, E is a constant. Okay, the interest is 3.5%, so you're going to do 0.035. Okay, and then you're going to multiply that by the time, which is 5 years. Okay, now let me show you on your calculator. You might not be real familiar where with E is. So one of the best things to do is, if you want to do E to a power, E shows up here, but it also shows up there. When it says E to the X, you can just go second of that LN key to get it that power to come out. That's what I do. So I'm going to put this in like this. So I've got 1,000. Then I'm going to go second LN to get E to a power to come out. Okay, now I'm going to go ahead and put this in parentheses. So I've got 0.035 times 5 like that. Some of these calculators may allow you to bypass those parentheses, but just to be safe, you need to put that in like that. So if I put that in using the continuous compound interest formula, well, I'm going to get something a little bigger. I get 11,091 point, and it's just a tad bit bigger. I mean, it's not much bigger. So, I mean, if you round that off, it'll be the same. But if you look at my previous result, it's a little bit bigger. So like I said, basically, the more often you compound, the more interest you earn, but it starts slowing down. Does that make sense? Okay, so that's as big as the interest can possibly be, is by the compound interest, continuous compound interest like that. Okay, everybody got that okay? And you know where the E is on your calculator and everything. Okay, very good.
1 second.
Yeah, go ahead. You got something?
Yeah, I don't know if I'm putting some right here.
Okay.
I just keep coming up with that right there. Did I not put that in right?
See, what you got to have is parentheses around the whole
entire,
thing.
The entire thing.
So
So boom, and then
have one
after that.
parenthesis
Yeah.
before .035 and one after 5.
Got you. Thank
That's
you.
why it's doing that. That's an important part that sometimes students overlook. So be sure when you do that, what he's asking about, you got to have the parentheses around the whole thing. One big parenthesis and multiplication inside. Otherwise, it's not doing order of operations correctly. Okay. Okay, I'll let you guys go ahead and do the next one. Just do one. This is continuous compounding, so you know when you're doing this formula, you need to do PR to the T power. That's because it says continuous. Just do that on your calculator, and let's see if we're okay. Okay, so let's see what we got on this. You see, you have a principal of 150, interest rate of 5.8. So you're going to change that and use 0.058. And it looks like the time is going to be 10 years. So when you do this, you should have just done the principal 150 times E, and then you're going to have 0.058 multiplied by 10. You have your parenthesis like that. So you should have got something a little bit bigger than 150. Is that what you got? Okay, that sounds pretty reasonable. Okay, so we'll do 150. I'm going to go second ln to get E to come out. And then in parentheses 0.058, and then times 10, and then we'll just round to 2 decimals. So that looks like, is that what you guys got?
Yes.
Okay, $267.91 is how you would round that up then. Okay. Okay, so that's how you use continuous compound interest. Any questions about that? Okay. Now, the next problem, I'm going to do something a little bit graphically. This graphically kind of helps you understand, I think, how interest works, and this will help you understand the next section, I think, when we get back into the calculus a little bit. So we're going to do this in our calculator. First thing that we have in this problem is we have our principal's 5,000, and they give us an interest rate of 5.61% compounded continuously. And when you see that it's continuous compounding, you immediately need to know, well, we're going to the Pert formula. So PE to the RT. Okay, we're going to use that formula. Now, what they don't do is they don't give you the time. So we're going to just graph this as a function of time. So let's write this down before we go to our calculator. Yeah, but we're going to graph to 4 years. Okay, we're not going to find 4 years. We're going to just draw a graph of how the time is changing. So we're going to use time as a variable, okay? Then we'll be able to figure out what 4 is graphically, okay? So what we're going to do is we're going to do this. We're going to put in the 5,000 in for your principal. Then we have E, and then change that decimal to 0.0561. Then you're going to put a T like that, okay? I think I got an extra T in there. So it's 0.561. And then T. Now you're going to have to put an X in your calculator like that. So we're actually going to graph this. So I'll go ahead and show you what you want to do, and then do this with me. So you can clear anything out that you have from your last example, and let's just put this in. So you're going to have to put this in like this. In Y1, you're going to put in 5,000. Then you got to go second ln to get that to come out, and then just to be safe, put a parenthesis, 0.0561, and then put your variable x in and close the parentheses. So that's what we're going to graph, and we're going to need to think a little bit about our viewing window here in just a second like that. So you want to get that set up like that to start with, okay? Now what they say in the problem is that you want to graph the first 4 years. So for the window, okay, what X represents is T, okay? You're going to have a time axis on this. So you're really looking at 2 things. This axis right here is T, or time, and then this axis right here is, a dollar amount, okay, that you have, okay? So what we're going to do is we're going to go from 0 to 4, because that's really what the problem says, and scale by 1, okay? Next thing you got to do is figure out how to do your Y. Well, to figure out your Y, just look at your table. Just go ahead and do like second graph, open up your table, and just see what kind of values you have. So see what this table is doing. It's kind of like a spreadsheet. It's basically after 1 year, this is how much money would be in the bank. After 4 years, there's how much is going to be in the bank, like that. So it looks like if we're going to graph that out, we probably need to go up to maybe like 7,000 or something like that. So for that reason, let's do this like this. We're going to do 0 to, say, 7,000. And that way that'll get good points and everything. Then probably scale that by 1,000. Okay, you figure that out by just looking up that information in your table. Okay, now draw a graph. So what you're going to see is you're going to see a starting point, and then you're going to see that thing increase over time. That's what you would expect to see, right? And if you went down your table on that, you would see that thing changing over time like that. Okay, so when we complete a graph, really all I'd want you to do on this is label that this is time and this is in years. You want to be sure that you label, you know, what's going on in the problem so somebody who's looking at the graph could make sense of it. So we're going to go out to 4 years, and then we're going to go 1, 2, 3, 4, 5, 6, 7,000, about like that. Okay? And then what I would do is just go to your table and just get enough points. So I'm going to open up my table. So it looks like at 0 we have 5,000. So 1, 2, 3, 4, 5. Like that. That's a good data amount. And then just pick maybe a couple other points. At 4 years, you're just a shade over 6,000, kind of like that, and so forth. So then you have, like, it's just going up a little bit over time. It's almost going to look like a line like that. It's not really a line. It's more of a curve, but that's what that graph's going to look like. And that's what you would expect is if you compounded, you're compounding continuously. But what happens, one thing I want you to see on this too, I want you to do one more thing on your graphing calculator, because it looks like a line, but it's not a line. So let's do one more thing. We've already got our graph. Go ahead and make your X max go all the way up to 100, like that. And then make your Y max a lot bigger, say, I don't know, I'll have to just, let's say something like 100,000. Okay, for your Y max, something like that. And then maybe scale that by, if you're 100,000, maybe scale by 10,000 or something like that. So I'm just saying, let's take this out to 100 years, and let's take the Y out a little further. Okay, let's see what that looks like. Okay. Okay. Now see, it's not a line, it's a curve. So remember that problem we did $25 and it ended up having over 3,000? That's why this is happening, is because it's an exponential curve. It kind of starts off low, but once you start getting out there 30 and 40 years, it gets out of control. And if you get out here, it's way up there. That's how interest works, because you're figuring interest on interest that's already earned. Does that make sense to everybody? So that's the reason why it starts low and then goes up like that. So it's a curve. Okay. The graph we drew didn't show that curve very well. That's because we're only going out to 4 years. Okay. Okay. Now I want to finish up with two other things here on this, and this is just doing the problem indirectly. This requires some algebra skill. I'm going to show you how to do this with technology and with algebra. So this problem says, how long will it take an investment of $10,000 to grow to $15,000 if it's invested at 9% compounded continuously? Okay, so this time, anytime that you're dealing with continuous, what formula do you write down? You write down the Pert formula. P equals P-E-R to the T. So if we're going to solve that problem, it's going to revolve around that formula. All right, now the first thing I want to ask you is, let's kind of see what everything represents in here. What is A in this problem? I gave it to you. Okay, that's what it goes to. Okay, I haven't given you that before, but this time we know this investment's going to grow to that. What's P? 10,000. You know that because you start with a number and it grows to a bigger number. Okay, your investment, your interest rate is going to be 9%. We don't know T. So we're going to plug everything into this formula. So if you do this, you want to write down A is 15,000, the principal is 10,000, and then you have E for 9%, you're going to use 0.09 times T like that. Okay, and I'm going to show you how to do this with technology and to use it with more of an algebraic approach. Okay, so you're going to figure out how long it takes for that investment to grow. Okay, all right, so the idea with this, and this is a very practical thing for savings and paying off loans and stuff like that. So you have to do this a certain way. The first thing that you always want to do, and this is going to depend on your skill with logarithms, which we're going to be working with a lot into next week. The first thing you must do is divide both sides of this equation by 10,000. Okay, and that's going to cross that out, and then that right side you're going to end up just having e to the 0.09t, and all these zeros cross out right there, so 15 divided by 10, that's just 1.5. That's what you get, and use your calculator if you need to, I don't care. But it's just as good to just do that in your head, okay? Now, what you have to do is you have to do logarithms, okay? And some of you are going to be shaky with logarithms. That's very common in a introductory calc class. So what you're going to do is you're going to take what we call the natural logarithm of both sides. Okay, so I'm going to do this to both sides of the equation like this. And there's going to be some things that I think you'll probably get a better understanding of in the next section anyway. Well, some of you have done this before in your past, some of you haven't. Okay, there's a property of logarithms that you learn that goes like this. And anytime that you have a logarithm of a number, and that number can be anything, and you have a power, it turns out that it's the same as doing that. Okay, that's a common property of logarithms. Does that look familiar to some of you? Okay, again, it depends on background issues. Okay, I'm just going to say this is a property for now without going through the details of that. I'll do that next week more. So what we're going to do is we're going to bring this thing down. Okay, then what we're going to have on the left side is we're still going to have ln of 1.5. You're going to have 0.09t and then times ln of e, because I brought that down. Okay, now this again is a background thing. Some of you may know this, some of you may not. Okay, do you know what ln of e is? Some people know. That's good. Not all of you do probably though. Well, what this means is a natural logarithm is a base e logarithm. And what a logarithm is it's just saying e to this power is equal to e. Again, we're going to do an intense review of this next week because we're going to have to if you're going to get with the calculus of this. So that becomes 1. So you have ln of 1.5 is equal to 0.09t, and then that thing just becomes 1. Okay. Now what you're going to do is you're going to divide both sides by 0.09. Then you're going to get your calculator out, and that'll give you approximately how long it takes for that investment to grow. Now that is all algebra background stuff. Okay. And it's going to be, some of you got it, I can tell some of you don't. So what we're going to do from here is we're gonna do this. We're going to just take our calculator, use the ln key, do ln of 1.5, close parentheses, and then divide by 0.09, and then that will give you the amount of time. So that's approximately 4.5 years. That's how long it takes for that investment to grow to that amount. Okay? Now, I think for a student in this class, at least at this point in time, if you know the properties of logarithms, this is something you can learn how to do okay. But like I said, you will understand this a little bit more in depth because when I get into the 11.2 section, I'm going to spend time reviewing logarithms. Okay, because some of you are going to need that a bunch. Okay, so we're going to do this graphically. In this section, you can actually do these problems graphically, but I want you to know how to do this both ways. So the next thing I'm going to do is just kind of repeat this problem, but then do it graphically. Okay, so what we're doing, we're still using this same formula. A is equal to PE to the RT. So we're actually going to do this. I'm going to go back to what we already had. The A was 15,000. That was given. The principal was your initial investment, which was 10,000. Then you have E. You have your exponent, which you have the 0.09. And then I'm going to put an X there because we're going to do our calculator. So let me show you what I want you to do on this then. And this will hopefully give you a sensible way to look at this problem with technology. So what you're going to do when you solve this graphically, you want to clear everything off, and you actually want to do these two things. You want to do, this is what you're going to put in y1, okay? And that's going to be 15,000, so that's going to be a straight line, right? Y equals 15,000 is a constant function, so it's like that. And then you're going to put y2, you're going to put that side. So let's do that. Put 15,000 in for y1, and then put in the formula like this, 10,000. And then open up the e, second ln, to get that to come out. And then put 0.09x. Okay, like that. All right? So what we're going to have is you're going to have a horizontal line. What do you think the e to the thing is going to look like? What has that been looking like? It's been doing this. When you have e to a power, it's a curve. It's what we call an exponential curve. So we're going to have everything put in like that first of all. Now for our window, you got to think through this a little bit. Okay, x is time. Our answer was 4.5, right? That's what we got algebraically. Well, let's just do 0 to 6, okay? I know the answer is 4.5, so that's why I'm going a little bigger than 4, okay? Scale by 1. Okay, now the other thing is, we know that that horizontal line 15,000, we need to go up 15,000 at least, right? Otherwise, we aren't going to see the line. So let's just double that and say let's go up to 30,000. Just need to definitely go up a little bigger than the 15,000. Okay, then I'll slide this over here, so if you need to refer to that and type that in. So that's how I'm going to get everything set up. And then when you type graph, you should see a horizontal line and you should see a curve. Okay, like this. So let's see if that's what this gives us. Okay, there's your horizontal line, there's your curve like that. Now that's what we would expect to happen. So what's happening in this is eventually that amount of money is going to catch up to the 15,000, right? So we can find the intersection to do that then, okay? So just do a real rough sketch of this, just so that you have this for your notes. So let's do something kind of like this, and I'll show you how to complete the problem. You can just sketch this. So let's say this is 1, 2, 3, 4. You don't have to have this super accurate, just as long as you label the key things. That's the time that's in years, and then over here is money, and then just have that as 15,000, and that's good enough. Okay, and then just kind of put your two curves, just sort of estimate that. You have a curve, and then you have a line like that. Okay, now I've done an example before where you find an intersection point, right? Okay, I think I've done that at some point in time in this class. So the way you're going to do this, and you want to write the keystrokes if you need to find this intersection point, which is what you're going to do, is you go like this. You go second, then you do trace, then you will find an intersection button. So once you have your graph established, go second trace, then it's option 5, where you do intersect. So you can type 5 or just highlight it and then press enter. So you do that. Got to do your keystrokes like that. And then what you do is, okay, you just need to get that cursor so it's fairly close to that intersection point. That's good enough if you get it like that. Then you're going to press enter after you've established that. When you do that, you should see a second curve go to the other graph. And then just press enter again. Then it's going to say guess, press enter again, and then it's going to start blinking at the intersection point. So what did we get when we got this algebraically? We got 4.5. See how that's coming out? Okay, that's telling you that that x value right there is 4.5. Okay, so that's what should be coming out on your calculator. All right, so what you get is t is approximated by 4.5. That's how you solve that problem with technology. Okay, that's a simple way to do that, and it's a helpful way to learn how to do it that way too. Okay, all right. Okay, does that make sense? What I did? All right, everybody okay? Okay, well let's do one more problem, then we'll take a break. Okay, this one we can do, we're going to do this one analytically, algebraically, and then we'll also do this one graphically. Okay, what this problem is saying is how long. So again, we're going to end up finding t, so we got to solve an equation. And then we're going to find out how long it takes for money to double. And notice I didn't give you the principal. I'm just saying money in general, okay, regardless of what your principal is. And we're going to have 4%. It's going to be your rate. And, of course, the continuous means that you're going to have to use your, that's the wrong formula, A equals PE to the RT like that. Okay, so you're going to use that formula. Okay, so ultimately, what you want to do on this is you want to get everything filled in. Now, it turns out that you'll get the same answer regardless of your principal. So if you started with $1 and then and you wanted the dollar to double to $2, or you could start with $10 and double it to 20, 100, 200. Guess what? It takes the same amount of time regardless. Okay, so it doesn't matter what you choose. For simplicity, I would recommend that you just put a 1 there and then double that so you get a 2. If I was asking the same problem with tripling, what would you do? 1 and 3. Okay, and you'll get the right answer. Okay, all right, so what we're going to have is, let's write down, we have 2 equals 1, e to the r is 4%, so you're going to use 0.04 and then put the t there. Now we're going to solve this algebraically exactly like I did the last problem. Okay, all right, so we're going to have this like this. This is just going to be 2 equals, and then the 1 doesn't even really have to be there. I put that on for emphasis, so you just do that. Okay, 1 times anything is itself. Okay, now there's 2 steps. You've got to use logarithms to do this. So what you do is you do the natural logarithm of both sides of this equation. Okay, so we do that. Okay, and then if you don't have the background, believe me, you'll get this, and you'll do this all the time in this class. What do you do with this exponent? And it's not because we're doing a derivative, it's because that's a property of logarithms. You can bring that down, okay? All right? And a lot of you have done this before if you had college algebra or finite, so that you're going to have 0.04t times ln of e, okay? So really the things that are kind of important is if you have ln of x to the n, that's the same as n times ln of x, okay? That thing can be brought down. The other thing that's kind of important is ln of e equals 1. We'll get into much more greater depth next week as to why that's true. So we're going to have ln2 equals 0.04t, because that thing goes to 1. Then you can divide both sides by 0.04. Okay, like that. Okay, then we get the calculator out, and we just calculate this. So if we do the calculation, we're just going to do the ln of 2. You want to be sure you close parentheses, and then divide that by 0.04. Okay, and then that's going to give about 17.3 years is how long it's going to take for that money to double. It would turn out that even if you put $1 million for the principal, it's going to guarantee it's going to take 17.3 years for any amount of money to double, even a penny. Okay, it's just the way it works. Okay. So let's do this one more time graphically, and I'll show you kind of how this goes in here. Now we're going to repeat what we just did, but we just need to change things a little bit. Okay? All right, so what you're going to do now is you're going to do this. If you look at what we set up this thing right here. This is what you're going to graph, is this thing that I'm highlighting right there. So in y2, just put 2. What's that going to do? It's going to be a horizontal line going through 2, correct? Okay. Then put this side in. You don't even have to put the 1 in. You can just go like this. You can go e to the 0.04 times t. Put your variable in. Okay, like that. So that's what you're going to graph. And you're going to get the same kind of thing, is you're going to have a horizontal line coming out, then you'll have an exponential curve coming out. Okay, that's what we're going to do. Now, you got to think about viewing window on this. So viewing window, our answer in the last problem was 17.3, right? So let's do something logical like this. Let's do x max needs to be bigger than 17.3. Let's just go all the way out to 30. Okay, whatever. Okay, that's kind of your call. Maybe scale that by 10. Okay, and then for the y's, well, at y max, you have to be at least 2, right? Everybody understand that? Because you graphed 2. Okay, maybe you double that and make that 4 or something. Okay, that's pretty. The point is, you need to be able to figure out those numbers. There's not one right way to do that. There's many ways, but you have to understand how the math works. So if you get that put in, then the next kind of key thing would be is just graph it, and then you can do the intersection command like I showed you how to do. So when you graph that, you'll have, there's your 2, there's the curve, and see, that's a curve. It's starting to get out of control, okay? So then you do your intersect command. So now it's just a matter of going second trace, option 5, okay? And generally the first, if it's pretty close, you don't have to move it. Second curve comes up, it's pretty close, just press enter. Then when it says guess, press enter again. Same answer. So you have 17.3, and then you have 2. So graphically, you can do any of these problems where you're finding time. And that's a good way to analyze and look at these problems and make sense out of it visually. What do you think? Okay, because that's the idea. It's basically, eventually this thing is going to hit any number. I mean, you could figure out how long it takes for that to go to 10. Okay, it's just eventually it's going to happen. Okay, because that graph of e to the power goes to infinity. Okay. Okay, now you don't have to put a graph on your paper unless you want to on that, but that's kind of the main ideas. Okay, well, let's go ahead and let's take a 10-minute break. So let's come back at 20 after. We're going to do a little bit of work with 11.2 and then a little bit of review.